Hi.
How you doing?
Hey, John.
Rick
How are
Reynolds.
you?
How you do? Good. Okay, we're set here. I'm going to untie that a little bit here. Sometimes these tends to get a little... Not the prettiest clip, but that's what they send us.
Okay.
Can you let that hang a little bit?
We're ready to go?
Yeah, we're ready to go.
Okay.
You bothered watching yourself on TV?
Oh, no.
Good. Okay, that's
I
your
wouldn't
program.
look at myself.
Are you going to introduce one here?
Yeah, I guess I will.
Okay.
That's someone else's recording. This gentleman here.
Hey, Chris. Good to see you. Yeah, we'll meet after.
Yeah.
Okay.
As long as there's no fan there.
Well, I don't know if it should be.
Yeah, I didn't hear anything when I said it.
Okay.
I do have a short bio, so.
Yeah, we'll go around there. So we can do that before you start moving.
Okay, if you want to do that, just let me know when you're ready to start.
Okay,
I start
we're gonna
screaming.
go like this. And this is-
Okay, you stand there. I'll tell you.
Okay, we're going to go, before I do the formal introduction of our speaker, we'll do introductions around the room, and that's also before we start webcasting. My name is Jennifer Dill. I'm a faculty member in the School of Urban Studies and Planning, and I help co-organize this, and I'll do more introductions with my colleagues in a little bit. But we usually like to, at least at the beginning of the quarter, introduce around the room so we all know who's here, and also so our speaker knows a little bit about the audience, so just who you are and affiliation.
I'm Amanda Snowden. I'm hopefully going to be a graduate of the program. Okay, my name is Erica Weiland. I'm in first year in our program specializing in community development.
And I'm Jim Carlock, and I'm a citizen that's interested in transportation issues.
Why don't we just finish on this side?
My name is Holly Stout. I'm working with economics in the term, and I'm very interested in city planning.
Chris Monsieur, faculty member in civil environmental engineering. Thank you.
Leslie Maryland, I'm a master's in urban planning student.
Matt Kaufman, Master of Regional Planning.
Daniel Laggard, community development.
Andrew Deere, a journalist and
Joe Kahn, student in the Civil Environmental Engineering.
I'm Hannah Capel, and I'm a first year MERP student.
Ben Zielke, visiting student from graduate student from DRIP.
Or natural, first year MERP student.
Ling Zhou from City of Portland, Transportation Planning.
Eric Rundle,
Tom Fester, second year MERP.
Steve Sigety, first year.
Sandeep, Masters in Civil Engineering student. Matt Burko, first year MERP.
Eugene Nucci, I'm a communications major.
Or Abby Hall, with interest in particular classes.
I'm John Levy. I'm an assistant professor in urban studies and planning.
Steve Hansen, Metro.
Along.
Cindy Pedersen with Metro.
And now we have Ken Duker, one of our emeritus professors, walking in the room. Okay, I am going to send around, this is the sign-in sheet for students, so I got almost all of you, but not everyone might be on here. So check to see if I marked you off. Okay. So now I'm going to wait to get the start the webcast, and then I'll do the formal introduction. Silent pause.
So we need a beep or something?
Well, this goes to the view.
Okay.
We're ready. Oh, there we go. Okay. So good afternoon. My name is Jennifer Dill. I'm a faculty member in the School of Urban Studies and Planning, and along with my colleagues, Chris Monsieur, John Levy, and Rob Bertini, we helped co-organize this weekly seminar. One reminder to everyone in the room, we do webcast the seminar, and we do it live, and then they're archived. And in order to do that, we need all of you who, if you ask a question, we want you to use the microphones in front of you. There is a sort of a button area that says touch. Touch that. Keep the red light lit while you're asking the question, so people who are watching on the web, and we do actually have people watch on the web, can hear your question. So please try to remember to do that. If you don't, I'll probably pipe up and remind you if I can tell. So without further ado, I'd like to introduce our speaker today. He is Zhang. He's an assistant professor in Department of Civil Construction and Environmental Engineering at Oregon State University. Did I get all that correct? And he's going to be talking about travel demand forecasting today. So welcome.
Okay, thank you very much, Jennifer. Thank you all for coming to the seminar. I really appreciate this opportunity to talk a little bit about my research in the area of travel demand modeling to you today. It's actually very hard to pick a title. So I think on the announcement, it may say the future of travel demand forecasting. That's probably too big of a title. So I changed a little bit to be a view on the future of travel demand forecasting. Okay, positive theory, behavior model, and process data. After the introduction around the room, I feel like not everyone here is working in the field of transportation planning or travel demand forecasting. So it might warrant a little bit introduction. So what is travel demand forecasting? What's travel behavior analysis? Okay. In short, travel demand forecasting try to derive system-level travel patterns, such as level of congestion, pollution emissions, traffic flow, okay, according to individual travel behavior. Okay, we're interested in individual choices that have an impact on travel patterns. Okay, those choices may include activity participation, destination, scheduling, mode, route, and a lot of other choices as well. And of course, travel demand modeling is a part of the transportation systems analysis. And we may also argue that when we do travel analysis, we have to also look into land use. Okay, in that case, we're also looking to firm and individual location choices, as well as accessibility changes over time. And furthermore, we can even look into the even broader economic system if we're interested in the integrated economic, land use, and transportation modeling. So in that case, we also try to estimate future economic growth in general, in specific sectors, and interactions between economic sectors. So this is kind of the general context for travel demand modeling. We need those models to tell us what the future traffic flow, what the future bus ridership are going to be, so we can evaluate and design policies or operations that either affect the travel or have an impact on travel demand. Before we try to discuss the future, I think it's probably a good idea to look into the brief history of travel demand forecasting. I try to make it as brief as I can, so I put everything on one slide. As you can tell, it's a very busy one. But here we go. In terms of modeling methodology, because usually we tend to believe the modern travel demand forecasting models dates back to the 1950s, so it's about 50 years old. So in the 50s, we have the urban transportation planning system, which we call a sequential model or four-step model. Now, with the advance in econometrics in the 1970s, we have discrete choice models. And even more recently, with advancing IT technologies, that really allows us to develop more sophisticated econometric models. So it allows us to do very sophisticated estimation on large data set. It also makes it possible to use computational process model, wherein we model the behavior and interactions among individuals in an urban area. In terms of data collection, okay, we have seen steady improvement in terms of statistical procedures in data collection in travel demand modeling. In general, we can see a trend from cross-sectional surveys to longitudinal surveys. So we're no longer satisfied with observing travel decisions at one point of time. We want to track behavioral dynamics. We also see advance in stated and revealed preference surveys, especially in the area of error control. And with the wireless technology and GPS technology becomes increasingly affordable right now for us to track individual behavior over time. Traditionally, we only have a 1 day or maybe 2 day or even 1 week travel diary. So with those advanced, with this advanced in data collection technology, we now enjoy an unprecedented data availability. Now, the most fundamental part, of course, is the behavioral theory. Now, that's a different story. I wouldn't say much about it right now. I'll just cite two of the well-known researchers in the field. David Du Bois, in his paper, says that the origin of the sequential model is, at the best, unclear. I think I agree with him, because if you look into the sequential model, at one stage we use the law of physics to model human beings, okay, for instance, in the gravity models. At another stage, we may consider rational behavior, rational choices, or individual behavior theory. So as you can see, there are some inconsistencies in the four-step models. Recently, we see a shift or a momentum change from trip-based sequential models to activity-based models or agent-based models. And Kitamura, okay, says that the efforts toward a travel demand model or travel behavior theory for the activity-based approach are in general fragmented. Okay, what he means is if you look at some of the activity-based models, we use utility maximization or rational behavior theory for part of the model. We may use heuristics for another part of the model. So we see a lot of hybrid analysis in those methodologies. And it's probably still true that we don't have a very good, consistent, coherent theory for activity-based approach. So that's kind of the history of travel demand analysis in a nutshell. An interesting comparison. And now I think it's really a time of challenges and opportunities for travel demand modelers and for transportation planners. Why challenges? Okay, the challenges are primarily due to increased political interests in various financing and operational policies. Okay, the history for capacity investment or for transportation investment in the U.S. sort of has a dividend point in the early 1990s. Before then, we were more focused on capacity improvement, okay, investing in new freeways. But after that, after early 1990s or late 1980s, planners realized you're never going to be able to build your way out of congestion. You have to manage congestion. Okay, that's why we see a policy shift. Right now, I'm more interested in innovative financing policies, including both pricing policies. You see value pricing, HOT lanes, okay, express lanes. You even see some private sector involvement in transportation investment now. And we need models that can tell us how that would affect the society as a whole and how it would affect different groups of population. We also see more and more sophisticated travel demand management policies. Okay, those policies may include flexible working hours, okay, parking incentives, or incentives for employees to take transit, and all those kinds of ways, policies that can affect travel patterns. So that's also a method to manage congestion and manage travel demand. Now, with the advance in information technology, we see advanced traveler information system becoming more and more popular. Okay? The idea is we can offer real-time traffic information to travelers so they don't have to sit in traffic, okay, sit in bumper-to-bumper traffic. There are also other information services that you will see or you have already seen in the transportation sector. Now, we also have a lot of advanced traffic management system which require travel demand models to be able to describe the evolution of congestion during the peak hour. Okay? And in many models, we don't have that capability right now. And from a system point of view, and a lot of you sitting here are city planners, urban planners, or land use planners. So you're also interested in a lot of land use policies, how land use policies will change transportation, and how transportation decisions change land use in return. Okay, in order to model these interactions, we also need to expand the scope of travel demand to include the land use system and economic system. And every modeler from Metro will tell me that they have limited resources. Okay. Now, we also have some interesting opportunities. Okay, as I just mentioned, we have advanced in data collection technology. Especially now, we have affordable process data. Okay, process data mean data that include observations of individuals at several different points of time. So we can actually model their behavioral dynamics, how they adjust their decisions over time. When another opportunity is the advanced in computing. Okay, now it becomes possible. I don't know how many of you have played the computer game SimCity. Okay, now it has actually become possible for us to simulate every individual and every firm, every organization in the city with reasonable computing resources. And finally, there are also some innovative modeling methods, or maybe I should say non-traditional modeling methods. They are not necessarily innovative. They are just innovative in transportation. They have been used in other fields for many years, but now we realize they also have substantial value in travel demand modeling. Now it comes time for an interesting comparison. Okay, now we have all those challenges because of policy interests. We also have these opportunities for us to move forward. In the 1990, Aggregate Pass was a well-known researcher in travel demand forecasting and planning. He published a paper in 1990 in the Journal of Transportation with this title. Okay, it's travel demand analysis and modeling in the doldrums. So at that time, travel demand modelers and even planners felt stagnation, okay, because the four-step model was capable of estimating various capacity investment policies. And there were no challenges or no additional resources for them to move forward. But after that, because of these new policy interests, okay, these new opportunities, we see a surge of newer generation travel demand models. And this is only a partial list of the activity-based models or computational process models. So it's an exciting time, really exciting time. So that's now. How about the future? Okay, modelers will tell you that you always need a little bit luck in order to get a very good forecast. Why? Because life is stochastic. The world is probabilistic, right? There is always some randomness you cannot capture in your model. So the conclusion, there are many possible futures. But today what I want to do is to share with you my view on a possible future, okay, based on my own research work in the field. Well, I think a possible future could include positive theory, okay, which is in contrast to normative theory. A normative approach would emphasize what humans should do. Okay, we should minimize cost. We should maximize utility. But what people should do and what they actually do could be very different. So the positive approach, on the other hand, emphasizes what humans actually do in the transportation system or in the broader urban system. Okay, you can imagine we need a lot more empirical studies in order to implement a positive approach. Process data, okay, is data revealing the decision-making process. Okay. And finally, behavioral models. So I believe that we need models that use empirically derived and empirically verifiable behavioral rules to represent human behavior or travel behavior. That's at the microscopic level, so where you study individuals. Then we will need some efficient computing algorithms for aggregation. Okay. Travel demand model, in a sense, is an aggregation process. Okay. It starts from a basic individual behavior theory. Then you use certain algorithms and models to aggregate those individual behavior to important system-level patterns. Okay. Now, the positive approach. Okay. I got into this with some interesting empirical observations that I think not very well captured by some of the existing models. Okay, the first one is human spatial knowledge is incomplete. Okay, we do not have complete knowledge about the city or about the transportation network. Okay, I don't know all the grocery stores in Portland, but I could still go to one. Okay, I don't know all the street, all the parking spaces in Portland, but I still have to make a decision as to how to come here and where to park with this incomplete information. So models assuming complete information may generate certain biases, as you can see later in the presentation. The second observation is that our spatial knowledge is developmental. Okay, when you first move to Portland, your knowledge about the city, okay, where the shops are, where the roads are, probably is pretty much zero. Okay, but over time, you will learn the city, okay, your spatial knowledge will develop. The third one, spatial knowledge is hierarchically organized. This is a little bit more complicated, but it essentially says that there are landmarks, there are major roads that we are more familiar with, and we tend to organize our knowledge around those major or more prominent landmarks or roads. And then we know that travelers only consider a very small number of alternatives among all the possible ones. Okay, this is similar to the first one. And we also observe that we do not want to collect all the information out there. Okay, there is information acquisition and processing and a decision cost. Okay, it takes time and energy to find out whether there is a better shop, whether there is a better job, whether there is a better house, and we take into account those things when we make travel decisions. Okay, then can our model capture that? Okay, we'll see. And when we search for alternatives, okay, when we search for a route to our office, when we search for a shop, and we know that search behavior is not random. So some of the very nice mathematical models may not be able to be, may not applicable here that assume random search behavior. And finally, there are behavioral dynamics. Okay, we may have provisional trial and error behavior first. Okay, we may try a new store, we may try a new road, and over time we will come to a more steady or a repetitive or habitual behavior. Okay, it would be good if our model can also capture that. So the theoretic work for the positive approach started from these empirical observations. So I really want to be able to incorporate these empirical observations into a theoretical framework, and then use that framework to develop models for policy analysis or for operational analysis. I think in order to capture those empirical observations, we really need a shift of focus. So as I mentioned, there are many different choice dimensions or travel choices that affect the final travel demand. So in the box on the top, you will see all kinds of travel and activity choices. Okay, participation, residential location, work schedule, auto ownership, mode, route, destination. All those choices can be individually modeled. Okay, you can collect data for each individual choice dimension, then find out which mathematical or modeling procedure is most appropriate, and then you try to develop models. Another method, okay, another focus is on the cognitive level. Okay, we can examine what kind of spatial knowledge people have and how they improve their spatial knowledge over time. Because after all, when we make all these kinds of travel activity choices, we use the same spatial knowledge in our head. Okay, we may even use the same heuristic rules or the same decision rules we've learned over time. So by shifting our focus to the observational level, to this cognitive level, we may be able to do more with less. Okay, there is a possibility there. Okay, but we'll see if it really works. The benefits are we have a common knowledge base and also a focus on the decision-making process. Instead of just trying to accurately represent the final choice, we can also model the decision-making process. Hopefully that can make our model a little bit more realistic and make our model a little bit more capable, okay, in evaluating different policies. Now here is the theoretical framework that I came up with. Okay, there is all kinds of information in the world. Okay, we can get those information from different sources, okay, from our friends, from web, from conversations, and most importantly, from our own experience. Okay. And all the information, before they become our knowledge, has to go through a learning process. Okay. and then it becomes a part of our integral spatial knowledge. Based on these spatial knowledge, based on what we know, what we have experienced, we may develop certain beliefs, may develop certain expectations. If you live in Los Angeles, if you live there for 10 years, you expect congestion. If you live in Corvallis for only a year, right now I don't expect any congestion at all. So your experience shape your belief and shape your knowledge. And once there is a spatial task facing us, we will use our spatial knowledge to search for alternatives. If right now you are asked to drive from Portland to a random restaurant, just think about your favorite restaurant. You have to pick up a route or pick up a mode. You will start using the knowledge you have and use probably certain rules, maybe individually different rules, to come up with a route, to come up with a mode, based on the knowledge you have and based on the expectations you have. Once you start searching for these alternatives, you can come up with certain alternatives. Then you will use a decision rule to decide whether you want to go with a new alternative or you want to stick to a road that you know or a mode that you know. And if you keep going to the restaurant, probably in this case, the journey to work trip is more appropriate because you have to go to work pretty much every day, every work day at least, if you're not a professor. Then over time, you will be able to adjust your decision, right? Because as you learn more and more about the network, you may be able to find more alternatives, and you may be able to adjust your decisions. And this is all dynamic. You can see time and space. These things can all change under this framework. So now the question is, this sounds like a reasonable description of decision making. But the problem is, can we actually derive rigorous quantitative models from this framework for our daily policy analysis or planning studies? Another question is, do we have the data sources or data collection methods to support the positive theoretic framework? These are the two topics I will discuss right now. First of all, about data. We can't do anything, do any modeling without good data. So this is very important. We not only want good data, we also want cheap data. And there are certain methods to collect process data. So as you can probably imagine that in order to implement this positive framework, we must have process data. A single observation, a cross-section observation is not going to be able to help us. We can use longitudinal or panel surveys to repeatedly to observe a certain individual's behavior at certain different time points. We can use GPS or other wireless technologies to track behavior dynamics over time. And we can use in-depth interviews to talk to people. A good way to find out how people make decisions is to talk to them, although this is quite expensive and may not be applicable in large-scale data collection effort. There are also some other methods, including memory recall, retrospective survey, and field experiment stated preference survey. I think actually I've applied these two methods to collect process data in the Twin Cities, which I'll explain in a little bit more details in the next couple of slides. Another method, which is not listed here, is to ask, use stated preference surveys to ask what people are likely to do if certain policies are implemented. That is very useful for a new policy. When you have a new policy, you try to implement a city. For example, if you are interested in congestion pricing, Portland probably haven't had a toll road before. And if you want to figure out what people would actually do when you have a congestion pricing, a good method is to use data preference surveys to randomly select a group of individuals and to see what their answers are, what they say they will behave. But all these methods have pros and cons, just like existing travel surveys. The first experiment that I did in Twin Cities is a memory recall retrospective survey. So essentially, this is a very cost-effective method to find out the decision process. You just ask a number of subjects, okay, through using either mailing, mail-out surveys, or using other survey methods. You ask them what their current choice is, and what their previous choices are. Okay, so you ask them to recall what they did before. Okay, and in this case, I have only 82 subjects. Okay, it's not a big project. Okay, it's actually, if everything that's done in this presentation was sponsored on a $70,000 project, so it's really not much. But as a demonstration of concept, I think it's good enough. We asked 82 subjects in the Twin Cities area, okay, what route they currently use for their journey to work trip, okay, and what route they have used or have considered in the past for that origin-destination pair. Okay, we actually collected more than one origin-destination pair. So that's one way how you can collect process data. It's actually very low cost, but there are possible recall errors. We may not be able to remember what we did before, but it's cost effective. So I will call this route search survey. So this is about how people search routes in a network. The next survey actually involves a field experiment. Okay. We asked about 117 subjects to actually drive 5 alternative routes between University of Minnesota and St. Paul Cathedral, which is the destination. Okay, why St. Paul Cathedral? It's a landmark. Drivers can't get lost, so they can see it from everywhere. We have freeway routes and 4 other alternative arterial streets. Their vehicles are instrumented with onboard GPS devices, so we can track their actual routes, and we can also calculate their travel time, number of stops, and all different kinds of route attributes. Then after the experiments, okay, and also the subjects drove these routes in random orders. Okay, so after these experiments, we asked the subjects which route they're actually going to use for different trip purposes. So this is a controlled environment. Okay, if you're interested in route choice, you can design an experiment to actually let them drive certain alternatives and look at how their decisions change as they get exposure to new alternatives. Okay, so this is controlled environment, and their behavior here may not be exactly the same as what they are going to do in reality. But a good thing is we only encounter moderate per subject cost and a low total cost. Why low total cost? Because you really don't need a lot of subjects in a controlled environment. I'll call this a route choice survey or route decision survey, okay, for the remaining of the presentation. So these are some of the methods you can use to get those process data. Okay, I know Metro is planning a longitudinal survey, which is also very good. And with the data and the theoretical framework, we have to find some good modeling methods. So the modeling work can be generalized in this single slide. So we first use these process data sets, okay, and use certain knowledge acquisition methods, and use these methods, okay, to find out what kind of rules individuals are likely to use when they make decisions. We try to empirically derive these behavioral rules from process data. So if it's about route choice, we no longer just assume they choose the minimum cost route, okay, however cost is defined. We want to find out what actually the actual behavior rules. And I also use Bayes rules to describe learning. So because we learn network, we learn space over time, and we need a learning model. Okay. And after we figure out the individual behavioral rules, I use agent-based simulation to aggregate those individual behaviors into aggregate or system-level travel demand patterns. Okay, why we need aggregation? Because we need to consider the interactions among travelers. Okay. Now, how do we model individual behavior? So here is an overview of the quantitative modeling framework. I've tried my best to remove all the equations because I didn't expect a lot of modelers here. But there may still be some here. I'll probably try to explain this quantitative framework without even touching those equations. So don't get scared. So overview. First of all, we try to use certain numerical methods to represent spatial knowledge. Okay? And if we want to develop a quantitative model, we have to use numbers to represent knowledge instead of just saying what the knowledge is, what knowledge is. And we use probabilities to represent belief. Okay? I believe there is no chance, okay, for me to find a better route other than I-5 to drive from Corvallis to Portland. Okay, that's a belief. Okay, that's zero possibility. Okay, there is a very good chance that I can find a very good store in downtown Portland. The grocery store in downtown Portland compared to Corvallis. Okay, that's also a belief which can be represented by a probability. And as I mentioned, we use Bayes' rules to describe learning. Okay, that's an assumption. Okay, you can use other learning rules. And I developed a concept of subjective search gain, okay, which is the subject belief of a gain or of what we can gain from additional searches for alternatives. Okay, I also developed a concept of perceived search cost. Okay, the search cost includes information acquisition cost, decision cost, information processing cost. So the search cost is the kind of things that prevents us to search all alternatives, to collect all available information. And finally, I use Ifthen Rules, okay, very similar to Ifthen Rules in your computer programs, to represent the actual search behavior and the decision behavior. Now, just for example, if we're interested in route choice, okay, the knowledge can be represented by a vector, which is the number of times travel conditions have been observed, okay, in our prior experience. Okay. And the probabilities is simply the subjective probability that an additional route search can return a route with a certain travel condition. Okay. For example, if in the past I've been able to go from my home to my office, okay, within 10 minutes most of the time. Sometimes when there is congestion, it could be 20 minutes. So this could be my belief. Okay? But then because of economic growth, because of road construction, because all kinds of things, the level of congestion may increase on my journey to work route. And after experiencing severe congestion, after experiencing congestion even on alternative routes, my belief may change from this prior probability distribution to this posterior probability distribution. Okay. And you can use numerical models to capture that. And also in the model, we track the experience and the beliefs and the knowledge of each individual in the city. Now, what's subjective search gain and subjective search cost? Okay, again, we could have a belief about the route travel time, okay, from home to work. If for a particular individual, that distribution represents his or her belief about travel time between home and work. And if currently the travel time on the route chosen is T2, which is very large, which is very long, and this individual will believe there is a very good chance to find a better route based on that subjective belief, right? And if that travel time is T1, so this person is already doing very good, so the incentive for doing additional searches is really very small, okay? So if the search gain, the subjective search gain is very large, we're more likely to search additional alternatives. But at some time, we'll stop. And I use perceived search cost to capture that. And I don't have time to cover the details, but you can actually derive the perceived search cost distribution among individuals empirically, okay, under this framework. And this is what I derived from the subjects in the Twin Cities. Okay, what does this graph mean? I pick a random point here. Okay, at this point, almost 90% of drivers, almost 90% of drivers will stop searching for alternative routes if the expected travel time saving is less than 20%. Okay? And similarly, we can obtain other perceived search cost according to this empirically derived distribution. And once we have the gain and the cost, we can assume that individuals will stop searching for alternatives if the expected gain may not be the actual objective gain, but the subjective gain is larger than the perceived cost. Okay? And in that case, they will search for alternatives. If the opposite is true, they will stop searching for alternatives. So this is a method to make it a little bit more rigorous when we model the search behavior, to consider when we model alternative choice and alternative search. Now, if a person decides to search for alternatives, this could be alternative destinations, alternative modes, alternative locations, alternative routes, I assume they use a set of if-then rules. Okay, why if-then rules? Okay, if-then rules, we see them in computer programming a lot. They've shown to be able to represent human decision process very well in the field of expert systems and expert systems engineering. Okay, and they are also very, very cheap to implement in computers. Computers are not very good at quantitative descriptions, but they are very good at implementing if-then rules. And we can use certain knowledge acquisition or machine learning algorithms to actually derive these behavior rules from process data. Okay, so there are tools for us to get those rules empirically. And from the route search survey I mentioned, we actually derived about 31 if-then rules to replicate the heuristics you use. You use, for instance, to pick a route between here and your favorite restaurant. You must use some heuristic methods in your brain to pick that route up from the spatial knowledge that you have. So these if-then rules try to mimic that process, try to replicate these heuristics empirically. Now, I don't have time to go through all the 30 search rules, but I think I do have some time to go through some of the decision rules. So this is when you search and when you find a new alternative, you will decide whether you want to use the new alternative or you want to stick to your current route or stick to your current alternative. This is for route choice. Rule number 1 says that if the travel time saving on the new route is larger than 39%, no matter what other attributes are, you will always switch to the new route. Okay. Rule number 2 says if its travel time saving is only larger than 11%, you will start to consider the pleasure of driving. Okay, you will change route only if the driving pleasure doesn't reduce significantly. Okay. The pleasure data is collected from the apt experiment survey. We ask drivers to rate the driving pleasure. And familiarity, we found that also drivers are more likely to use a route they are familiar with. If you have traveled on this route before, or if you are used to driving on that route, you are reluctant to change. Okay. And we can validate those results because estimation is important, validation is also important. There are also methods for us to do systematic rule validation using a separate validation data set. Now, once we figure out the search, the knowledge, the belief, the search process, and the decision process, we need a good methods to aggregate these individual behaviors into aggregate demand patterns. I found computer simulation is very useful in this case, especially agent-based simulation. In these models, each individual is the basic unit of analysis. So each agent is a class, if you're familiar with computer programming, and you can store their knowledge, their belief, and their decision rules as an individual decision agent. then try to simulate how they behave in the city and how they interact with each other. And on the left-hand side, it's basically the positive theoretical framework I talk about, except now they are replaced by a quantitative model. On the right-hand side, we need a network model. So because the focus of this research, with the limited resource that I have, is on the behavioral side, so I used the simplest network model that can work, which is the BPR cost function. But of course, you can use more advanced computer simulation models or dynamic network models for this part. And so everyone in this work, so in the initialization step, everyone has zero knowledge in the city. And they will learn, they will search for alternatives, they will choose alternatives, and they will interact because they create congestion, and there is also information exchange. At a certain point, the system can achieve a possible equilibrium. This is the equilibrium when everyone stops searching for alternatives and stops changing their decisions. At that stage, the system achieves an equilibrium, maybe. And we'll see if that equilibrium can be achieved or if that exists at all using numerical simulation. I call that equilibrium behavior user equilibrium, in contrast to equilibrium under normative assumptions such as deterministic or stochastic user equilibrium. Definition, as I mentioned, is defined as the state when all travelers stop searching for alternatives and form repetitive travel behavior. Because for each traveler, the perceived search cost exceeds the expected search gain from additional search along every possible choice dimension. Now, we can show that this equilibrium exists numerically. We can also show that this equilibrium is not unique. What does it mean? What does it mean that equilibrium is not unique? It means if you use different starting conditions, you will get different results. An equilibrium is unique means no matter where you start, you also get the same unique equilibrium. This BOE is also not stable because historical dependency, by definition, is built into this model. If you change the system, for instance, if you raise the price, let's say if you charge people if they travel on I-5 in the Portland area, if you make everyone pay $5, then the next day or the next year, you cancel that policy. The equilibrium being not stable means you will not get the same travel pattern before the original policy. Because when you implement the policy, drivers will change routes or change destinations. That will change their knowledge. You will not be able to get original state back if the equilibrium is not stable. Now, some researchers may think non-unique and unstable equilibrium is not desirable. But I would say, my view is that in reality, we don't have stable and unique equilibrium. We do have historical dependencies. But one can argue either way. I guess probably the next question is, since you are simulating so many individuals, I'm even trying to simulate their brains, is it possible to actually implement a model on a large network? Am I good on time? Because I don't know when it ends. I have probably 10 more slides. I demonstrated this model on the Twin Cities network in Minnesota. It's about 3 million population, about 8,000 nodes, just above 20,000 links. And during a typical peak hour, there were about 600,000 individuals using the transportation network in a typical peak hour. Now, how do we measure convergence of the model? We can simply use the total number of travelers still searching for alternative routes, and the total number of travelers still changing routes in the system. As time goes on, more and more drivers will become satisfactory with their choices, and we do have a BOE achieved after 20 iterations on this network. A comparison of the observed distribution of number of routes considered by travelers and the model predicted number of routes considered by travelers. Okay. If you put in normative models here, normative models assume perfect information. Okay. They assume drivers know every single possible routes, which is typically thousands or even tens of thousands. Okay. So this is, I would say, at least more realistic in terms of behavioral realism. There is also a very interesting summary statistic if you use the positive approach. Okay? Because in the positive approach, we do not assume perfect information. So the choices people make are not perfect, okay, from a normative perspective. Okay? They are not necessarily using the route with the minimum travel time. They are not necessarily use the alternative with maximum utility. So you can get a statistic to describe the difference between their actual choices and the choices they should have made. Okay. In this case, for the route choice, we can use the average relative access cost. So this number means, okay, 18% means if a driver in Twin Cities can get perfect information about real-time congestion, that driver will be able to save travel time by 18%. Okay? But this doesn't mean if everyone can reduce their travel time by 18% if they have perfect information, because that leads us to DOE. Okay? If everyone have perfect information, that's not necessarily the best case from a system perspective. So using this kind of models, you can look at the value of advanced travel information systems. Using normative model is very difficult because they assume perfect information in the first place. And it also allows you to derive actually the dollar value, okay, for the benefits of information services. Now, how about computational properties? Actually, we found the BUE is much more computationally efficient than DOE and BUE models. I have multiple lines here because the convergence properties of SUE and BUE both depend on certain parameters. Okay. And so it's actually not computationally more expensive not necessarily more expensive, computationally more expensive when you increase or improve the behavioral realism of the model. Okay. This may be a little bit counterintuitive, but that's the result. And how about the actual flow patterns? Okay, does it actually make a difference if you use the positive framework, if you use assumptions that are closer to reality? And this is the 45-degree line. If all the dots align on this 45-degree line, it means there is no difference between normative models and positive models. But we do see significant deviation from this 45-degree line. So there are some differences. And then the next question is, are those differences systematic? Okay, if they are just random differences, I don't think we need to care about that. This graph shows the estimated level of congestion. Okay, this is a distribution of volume to capacity ratio. Higher volume capacity ratios means higher level of congestion. Okay, low volume capacity ratio means lower level of congestion. There are some differences, but I really want to draw your attention to this part of the graph. This may seem a very small part of a graph, but this is actually the most important part because these are the high flow links, or the links with the highest level of congestion. And the observation is that if you make normative assumptions, you will likely underestimating the level of congestion on the most congested links. Okay, why? There are a couple of reasons. First, incomplete information. So on the normative models, we always assume that when the level of congestion on a certain route becomes higher, drivers will be able to minimize their loss by switching to alternative routes. But the positive model suggests that in many cases, even drivers experience increased level of congestion, they do not necessarily switch to an alternative route because they don't have incomplete information, because they are reluctant to change, they are reluctant to search, and because the heuristic rules they use in alternative choice are not optimal. Okay? So this may be a little bit disturbing, and I think it definitely deserves further investigation because it has important implications. Okay, if there are differences between normative and positive models, if there are differences between these two approaches, do those differences actually make a difference in policy analysis? So that's what planners are interested in. They also use this for a traffic operations study. Okay, Twin Cities, like Portland, also has a lot of RAM meters, okay, the traffic signals on the freeway entrance ramps to optimize traffic and try to reduce congestion and improve safety. So this is the hypothetical scenario, but we do have data to back that. The scenario is, the before scenario is a transportation network without any RAM meter. Okay, the after scenario is 443 RAM meters are installed in the Twin Cities. Okay, we want to know if that can actually improve things. Okay, if it does improve things, who benefits? Okay, who will lose from the policy? So when we apply the BOE model or the positive model, we found out that for the whole area, only about 3,000 drivers will actually change routes. Okay, once you have RAM meters, okay, think about it. When you have the ramp signals, they are likely to benefit those who drive long trips on freeway mainline, right? But it likely will hurt those who drive very short distance on the freeway because now you have to wait for a significant amount of time before you can get on the freeway. And these drivers will also switch routes, which may affect other drivers on arterial street. Okay? Although you only install signals on the freeway, it could affect everyone. Okay? But only about 3,000 drivers will switch routes on the first day. After about 6 weeks, the traffic can achieve a new equilibrium. If we look at impact, the individual impact, okay, this is the distribution of travel time changes for individuals during a typical peak hour. If you use the positive model, the BUE, it suggests the total travel time will increase by 0.3%. If you use normative model, for instance, deterministic user equilibrium, total travel time is shown to decrease by 2%. So we have opposite conclusions. Okay, why? And these numbers look very small, right? 2%, 0.3%. But when you multiply that with millions of individuals by 365 days a year, that's usually $7 million savings in each year. Okay, so that's significant. And upon further investigation, we come to this conclusion. Maybe I should have put a quotation mark on exaggerating, okay, because maybe modelers are exaggerating unknowingly transportation policy and project benefits. Okay, why? Based on the positive theoretic framework, okay, those who benefit from a policy change will always get that benefit automatically. Okay? But those who are hurt by the policy, okay, under normative assumptions, okay, they are assumed to be able to minimize their loss by adjusting their behavior in an optimal way. Okay, they are also assumed to have perfect information to deal with the loss according to the policy. But our results suggest that in many cases, many individuals who are hurt by those policies or new operations policies will not change their alternatives, will not conduct these behavior changes, okay, because, again, they don't have complete information. There are costs associated with searching for alternatives, and they don't want to change the alternatives. There are behavior inertia, and they are also they use heuristics. They probably don't know what the optimal solution is. So if this is true, that means normative models will systematically overestimate the benefits because it systematically underestimates the loss, okay, for these specific population groups. So some general conclusions from this research effort. We proposed a positive approach, including the theoretical framework, data availability, and some modeling methods. It's demonstrated and it's fully operational on large-scale networks. And also a byproduct, a new traffic assignment model, not bad. And we also found different behavior assumptions can result in different demand estimates, and even opposite policy recommendations. Okay, that definitely deserves further investigation. And we also found that process data can improve the behavioral realism, and they are affordable. Okay? And we also tried some unconventional modeling methods, and it seems they are appropriate. Okay, going back to the title of the presentation, okay, a view on the future. Okay, we're always interested in the future. So I'll actually discuss a little bit about the perfect travel demand model that everyone or every planner wants. Okay, we want a model to be realistic in terms of behavior. Okay, we want a model to use very realistic assumptions. Okay, to actually replicate what's actually going on in the world. So we want behavioral realism. Okay, we also want practicality, which means the model doesn't require us to spend a lot of money to collect the data. It doesn't require a lot of efforts or unacceptable efforts for modelers to maintain and operate the model. So we want it to be practical. We also want models to be policy sensitive. Okay, what does that mean? That means we want a model to be able to evaluate or to help us design all kinds of policies, okay, that we're interested in. Okay, we want policy sensitivity. We also want predictive accuracy. Okay, we want the model estimates to conform with reality very well. And many will say we also want a model to be rigorous. Okay, what does it mean to be rigorous? Because we know that modelers are human. Human can have errors, judgment errors, can have mistakes. And a rigorous model, okay, a very rigorous model would make sure that as long as you begin with a certain set of assumptions, you work, no matter who is the modeler, okay, they will always achieve the same conclusion, or they will always get the same result. Okay, if the model does that, we say it's very rigorous. Okay, usually the models with unique mathematical equilibrium properties can be considered as rigorous. Now, under this context, we can take a look at how the policy approach may have an impact, okay, in the future. Okay, this is my thoughts at this point. I think because now we consider the decision-making process in detail, we can help improve the behavioral realism of our models. Okay. With better representation of behavior, we can also estimate a broader spectrum of transportation policies or even land use policies if we use an integrated land use or transportation model. And for instance, advanced travel information technologies, I've also used this approach to develop models to look into congestion pricing and the involvement of privatization. So you can also do that. With regard to practicality, I put a negative sign there with a question mark. I guess I really like one saying that I learned from one of my college professors, that you always get what you paid for. You cannot expect improvement without any cost. Okay? But as long as that cost is justified, okay? It could be different for different modeling agencies. Okay? If you do have a lot of needs, if you really want to improve policy sensitivity, if you really want to improve behavioral realism, I think it probably justifies additional cost in data analysis and data collection. With regard to predictive accuracy, okay, we have to conduct more analysis. Okay? The conventional wisdom is that if the model has better behavioral realism, it should have better predictive accuracy. But that's not necessarily always true. It depends on the kind of data you have. Okay? So we need to conduct additional analysis on that. With regard to rigorousness, it's very similar to existing activity-based models or computational process models. There are randomness, Markovian variability built into the model, so I wouldn't say it would have any significant impact on rigorousness. After all, modeling and planning is an art of compromising. Okay, you want everything, but that's just not impossible. So every modeling agency has to decide on their own what they want, okay, to justify their expenditures. But if we can improve the model or improve the theory, the data collection methods, and modeling methods, that should be able to help agencies in general and in many cases. So with that, I think I'll stop, and I really appreciate your questions or your comments or even your views on the future of travel demand modeling or your view on the future of urban planning or city planning. So I guess that's all.
And I'll remind everyone to use the microphones.
Yes. Okay.
Questions?
Yes, could you comment on your aggregation method?
Mm-hmm.
I'm a little puzzled in this application. Were you applying your individual models to a set of synthetic population?
Yes. Yes. You need a population synthesizer because when we estimate these behavioral rules, we use a sample population. And when you try to estimate the system level impact, you have to generate a population that's representative based on usually census data you have to write. So the answer is yes.
Was SILK an acronym for something? SILK theory?
Oh, yes. It's an acronym for, it's an interesting story behind that. But it stands for Search, Information, Learning, and Knowledge because we emphasize these behavioral elements in the approach. Yep. Hey, Zhang.
This is actually an area that interests me a lot. When I was first doing my dissertation proposal, I was doing this exact same type of thought process. And then my advisor was more of an econometrician, took me by the collar and yanked me back into econometric land. But I did do a lot of literature review and studied computational process models and cognitive psychology. So I really like what you're doing because I wish I would have done a little bit more of that. At the time, I was interested in doing planning models. So it's looking at how cognitive psychology later on how people plan their day, not just wayfinding with route choice,
Right.
the whole day, where they go, which activities. My first question is, do you feel that this approach can be extended to get into the whole demand side of the part of travel demand modeling?
Okay, very, very good question. I asked myself that question a lot when I was working on this as well. It's very good to know that you're also interested. I do have slides here. I think it could be used. Okay, I thought about that. I talked to a number of persons. The reason I didn't incorporate in this research is because I don't have good process data to look at other choice dimensions. Okay, that's why I didn't incorporate this. I talked to Theo Ahrens and some others, and what I'm doing right now is to extend this to scheduling choice. Okay, with some data they provided. So my feeling is we don't know 100% sure, but I think there are definitely the possibilities here. So that's why I'm very excited to learn that Metro is willing to is planning on a longitudinal survey, albeit postponed a little bit. But I think we can definitely try this if we have good process data on these other choice dimensions. I'm definitely willing to discuss with you more on these possibilities or any recommendations you have. So at this point, I don't know for 100% sure, but I'm definitely willing to try. Okay, so this is sort of my plan. Okay. Right now I presented route choice. I do have some other spatial choice elements developed. I just moved that to include temporal spatial choices. And finally try to expand that to all travel-related choices. But that's the plan.
You'll be busy.
Yeah. Yes.
I noticed you mentioned building your way out of congestion. Could you just comment on whether or not it's possible the considerations involved in building your way out of congestion?
There are actually some very interesting studies conducted by FHWA and also by Minnesota DOT that I'm familiar with. They conducted an estimate as to how much money you will need, okay, to ensure that all roads have level of service B 20 years from now. Okay, level of service B usually means no noticeable congestion at all on all roads. Okay, you can actually use construction maintenance cost models and the travel demand models to find out what that dollar value is. Okay, for the Twin Cities, they estimated that Minnesota DOT would at least need $8 to $16 billion in the next 20 years to build their way out of congestion. Okay, just to put that number in context, for the whole state of Oregon, the Oregon Transportation Commission expects only $1 billion or $1 to $2 billion for the next 8 years or 10 years for capacity improvement. So it's just financially impossible, at least by the public sector, to build additional capacity to resolve the congestion issue. That's why I guess we got our jobs to try to manage congestion, try to plan the city better, try to look into other alternative modes to help mitigate this issue.
Are there any examples of other alternative modes actually reducing congestion?
Sure. If you look into the literature, if the theory is, if more people are using alternative modes, we'll have less vehicles, we'll have fewer vehicles on roads. So I would say it's not very difficult to make the case. And if you look into mode choice models, you can easily demonstrate that in the model. But to do it empirically in a city, it's a little bit more difficult because you don't have control over other factors that affect transportation. Some cities may do very well in the transit area. I know Portland is one of them. You may still see increased congestion. That's probably not because of the alternative modes, but because of the overall economic growth or overall land use growth in the general background effect. So it's very hard to do that empirically. I don't know if any of us sitting here know an empirical study on that, but it's very practical to show that in a model. Okay, of course, the models are empirically estimated and verified, but I don't know empirically how you can do that very neatly. Does that answer the question?
Yeah, I guess it does. I'd love to spend an hour talking about this, but we can't take up the time.
Okay.
Thank you.
Can these route choices be made available to the common?
To what?
To the common people, so that they can select their routes.
Mm-hmm. What do you say, common mean?
I mean, the public, to motorists, travelers
Mm-hmm.
who are using it.
Okay. So let me try to rephrase it. Are you trying to say if we can make the information or make route choice, or are you talking about advanced travel information system or ways to inform travelers about routes in the city? Okay. Definitely, because now in the model, actually I've used it to estimate the value of information service. Because right now, we don't have perfect information. For instance, one result directly from this research is that, in the Twin Cities, at least according to this model, an average person or an average driver in the Twin Cities can reduce their travel time by 18% if they have real-time information. If your travel time to work is, let's say, 20 minutes, then 18% reduction would be 3.6 minute reduction in time every day. If depending on your income, your value of time, let's say $10 per hour, you can calculate the amount of benefit you can get from that kind of information service. So I would say, yeah, you could apply it to information system analysis. Yes. Yes. Question.
What kind of research would you like to do next with this model? I noticed that you say up there about expanding it to temporal and spatial choice.
Mm-hmm.
What kind of research would you want to do to expand it?
Okay. I want to do all kinds of research to expand it. As I said, you can't do it without data. So right now what I'm trying to do is really to collect good process data, or either collect or try to get it from other sources, and see if we can use the same theoretical framework to develop these models of these choice dimensions, and if we can integrate them together using a consistent spatial knowledge structure. So the benefit of this approach should be really seen when you have multiple choice dimensions, because you only need to maintain one spatial knowledge structure for each individual in the model. So I definitely want to do that. right now I'm a little bit busy with another project on congestion pricing and road privatization, but that's definitely something I want to do in the future.
Could you give a few examples of private investment in the networks? You talked earlier about the public not being able to build its way out, and you're seeing some private investment. Could you just give a few examples of that?
It's a recent phenomenon, and it's very interesting. We don't have to go to other places. If you look at Portland, I think this area is considering 4 sections of the network. I think they probably have a deal or is in the discussion that if you talk to people in the ODOT, Office of Innovative Financing, I think they're discussing the possibilities of having private companies to invest in 4 new private toll roads in the Portland metro area. Some others may be able to add more to that. In other places, Chicago just sold their Skyway for $1.9 billion. To a private company, and they'll charge toll on the roads, and they'll maintain the roads. And you can also see private toll roads in Texas. And there are some other ways to change the ownership structure. Okay. In Colorado, what they do is they actually established a new agency that is sort of independent of the Department of Transportation. They allowed that agency to manage all the toll roads or express lanes in Colorado, in Denver. So there are different possibilities. And as because public agencies now all face budgetary constraints, they cannot build roads to accommodate travel demand. Although modelers, planners, including city planners, are doing what we can to try to mitigate that issue, but eventually we'll probably still, at least at this stage, we'll probably still need certain capacity improvement. And private sector certainly has interest, and we're certainly interested, as modelers want to know the impact on the society in general and the impact on different groups of population, especially people with different income or people living in different regions. So there are examples right now in the U.S. And public-private partnership, I think, is a very hot area right now. At least it's an emerging issue.
We've got a web question, so we always like to get those in. So to what extent does the reliability of travel times impact travel behavior? Do travelers effectively recall the variability experience and use that for route choice?
Okay, reliability. Now, in some of the results, okay, some of the rules, as you can see, familiarity is a factor. Okay, we didn't measure the reliability directly in our experiment. So I try to answer that just from this research first, then probably share with you a little bit my just general feeling about that issue. And we asked, because we only asked the subject to drive these 5 alternate routes once, so we can't measure the reliability factor. But we do use a familiarity factor. So if you are more familiar with the route, okay, it's more reliable because it's less likely you were driving the wrong direction or because you know what the average level of congestion is. But we do see familiarity as a very important factor in our behavioral rules. Okay, so I would say even these results, okay, not intended to look at a reliability issue, show that reliability could be an important factor. If you talk to researchers like Anthony Chan or others, they're really into reliability, and I think we have a conference now on the International Symposium on Transportation Network Reliability. Many empirical studies and theoretical studies show that it's very important. When we choose routes, we don't just consider the average travel time. We also try to consider the variation of travel time. So, because variation is very important. If you go to airport, you want to pick a reliable route. Although you expect the average travel time is 10 minutes, you probably were budgeted in 20, 30 minutes just because there is a possibility of a congestion or an accident. So I think that's a really important area, which I could do more. Mm-hmm.
Okay, I have a question about, you were talking about the historical basis of variable and travel demand modeling. And what about the idea of, in the future, impacts of higher oil prices and or supply shortages,
Mm-hmm.
do you think there's any possibility of there being a decrease in congestion due to resource issues, and what would that mean for travel demand modeling?
Okay. You look at supply and demand. If you raise the price to a sufficiently high level, you will always get lower demand. Okay. Some empirical studies show that the price elasticity, price elasticity of oil is not very high. So if you raise the oil price by 20 cents, 30 cents, it's not going to have a major impact on congestion or on travel choices. But if you raise it high enough, it certainly will. But when will that happen? I don't know. But we talk about oil peaking a lot. So we should expect that. I think agencies should be prepared maybe to start working on certain research, do some modeling work to look at what the potential impact will be if we have very high gas prices or we have gas shortage, and how we can prepare our city for this scenario. Okay, it could be 10 years from now, 20 years from now, but we know oil is a scarce resource. It's non-recyclable. That's what I want. I guess that's what I want to say on that topic. Yes.
One of your slides showed kind of a stagnation in the 90s on modeling, and then kind of the next list of all these up-and-coming models.
Mm-hmm.
Are there some that are starting to incorporate some of the ideas that you've talked about today?
Oh, yeah, definitely. And a lot of them are computational process models. They also simulate individual behavior. And Metro has tested the transit model, which also simulate individual route choices. But they, in general, I don't think they have a consistent positive framework. I have to say that I borrow a lot of ideas from a lot of previous researchers. So I would definitely say yes. Some of the ideas have been used in other work.
Any last questions?
Yeah.
Mm-hmm.
You've kind of touched on this before, and that's, do you personally foresee greater privatization in urban centers of toll roads, like in the city?
Well, in private roads in urban center, I think it's okay. If I think of myself as a transport economist, I would say probably yes. Okay, I don't have the slides with me right now because I only brought a little USB drive. Because we actually tested this welfare impact of privatization in urban areas. Okay, as long as if you privatize roads without any regulation at all, that's a bad thing. Okay, but if you can use some proper regulation policy, the one that I tested is a very simple price ceiling policy. So the private sectors can build roads, okay, but they cannot charge tolls higher than a certain ceiling price. Okay, if you change the ceiling price, you can see the impact on social welfare, and that actually does a very good job if you have a proper ceiling price. So with proper regulation from economic point of view, I don't see any reason why we definitely don't want that. But there are other concerns as well. Okay, safety is one. Okay, this happened in the railway industry. Okay, when the British railroads were first privatized, I think 4 or 3 fatal crashes occurred in the system within a month, and then the government bought it back immediately. So safety is a concern. And the general public and some users simply believe roads should be free. Okay, we want freeways, right? So politically, there may be some, it's not very palatable in some cases, but there could be some extreme scenarios when that could happen. So it's not only an economic issue, it's not only about the social benefits, it's also a political issue, it also has to do with safety concerns and other regulatory concerns. So it's very complicated.
Okay, with that, we'll wrap it up. But before we thank our speaker, I'll put in a plug for next week. And so speaking of the end of oil, and next week's speaker is from the firm Sequential Biofuels, and he's going to be talking about biofuels for air quality, energy security, and economic development. And with that, I want to thank Zhang for...
Thank you.